Добрый день, уважаемые слушатели. На прошлом занятии мы с вами рассмотрели видеоурок, в котором рассказывалось, как считать фазовый состав по программе термокалк, как задавать параметры, принцип работы и какие данные нам для этого нужны. Сегодняшний наш видеоурок будет посвящен построению поверхностей Liquidus и Solidus в многокомпонентных системах с помощью данной программы.
In this video, I'll show you how to use the batch calculation type in the property model calculator to calculate solidus and liquidus temperature. The batch calculation type allows you to upload a data file directly to the property model calculator, so you can run calculations with significant amounts of input data. You can also include experimental data in your data files, so you can compare experimental results to calculated data, as we will do in this video. The example in this video uses a demo database, so it can be run by anyone with a full license for ThermoCalc 2021b or newer, regardless of which databases you have. It cannot be run with the free educational package because it uses more than 3 elements. This calculation is based on example PMG12, which is included in your software and can be accessed from the Help menu, Examples files, Property Model, General. In this video, I will walk you step by step through setting up the calculation, and I will discuss the batch calculation type and the results. A data file is included in the Examples folder of your software that you can use to complete this example. To begin the calculation, select the Property Model Calculation template from the home screen of ThermoCalc. This will load all the nodes we need for this calculation. From the System Definer node, select the FE Demo database. Then select the elements iron, chromium, manganese, nickel, and carbon. The composition will be set using our data file, so we will not set it here. Select the Property Model Calculator node. From the General Models library, select the Liquidus and Solidus Temperature Property Model. If you click on the Description tab in the center of the window, you can read a description of the model and get information about the various settings and how to configure the calculation. From the top of the window, we will leave the composition unit as mass %, but we will change the temperature unit to Celsius. Our data file includes this information, but it is advised to set it here as well because the program will use this when it is missing from a data file. Again, the material composition will be defined in the data file, so we will leave it as it is. The batch calculation type allows you to set a timeout that is applied to each row of your data. This means that if one of your rows of data is incorrectly formatted, or the calculation is complex and may take a long time to run, the program will skip over a row after a certain amount of time and continue with the rest of the calculation. We will not use this option for this calculation, so leave it unchecked. We will accept all of the default values for the configuration. You can read about these configurations in the Description tab. Under Calculation Type, select Batch. When we do this, several fields appear that allow you to upload and configure your data. For example, you can enter the file path to your data file, or you can select the folder icon to navigate to it. The program accepts data in the form of CSV files and spreadsheets from a variety of programs. There is also a drop-down menu to set the delimiter when you're uploading a CSV file. This should be set before you upload your data. We'll be using a CSV file that is comma separated, so keep the default setting of comma. Next, select the folder icon and navigate to Documents, ThermoCalc, Your Software Version, Examples, Graphical Mode, Property Models, General. Select the file PMG12, Solidus and Liquidus Batch Calculations, then select Open. The data appears in the form of a table so it can be easily read. This data is a synthetic set of experimental data points. There are columns for each of the 5 elements we set in the system definer, populated with compositions of almost 50 alloys. Next is a column for the composition unit. The program allows you to use different composition units in different rows, but in our example, we are using mass % for all rows. The last 2 columns are experimental data for liquidus and solidus temperatures. In the batch calculation type, when a column header includes EXP, the data in the column is treated as experimental data. When the calculation is run, the experimental data will be plotted against calculated results. To learn more about how to label column headings and configure data, go to the Help menu, Online Help, and search for Batch Calculations. The program validates data prior to running the calculation to ensure that uploaded data is formatted correctly. For instance, if we were to change the chromium content in row 2 from 2.3% to 200.3%, we would have a system greater than 100%, causing the dependent variable, in this case iron, to become negative. When your data has issues like this, the Perform button will be grayed out and you will not be able to run the calculation. If you hover your mouse over the button, a tooltip appears listing the issues and offering tips on how to solve them. You can choose to skip the validation and run the calculation with errors by checking the Skip Validation box. Our data is formatted correctly, so we will leave the box unchecked. Next, select the Plot Renderer node to configure the plot. From the right side of the panel, select Cross Plot Mode, which allows us to compare the experimental data to calculated results. Set the x-axis to liquidus temperature, which is the calculated results the program will generate, and set the y-axis to experimental liquidus temperature Celsius, which is one of the sets of experimental data we uploaded. Under temperature, set the unit to Celsius since the experimental data is given in this unit. We want to show the limits of the root mean square error in our plot, so check the box next to Show Limits and select RMS from the drop-down menu. We will now plot this portion of the calculation, so click Perform at the bottom center of the program. Once the calculation is complete, your plot will appear in the Results pane. This plot shows a cross plot of the calculated versus experimental liquidus temperatures. The solid line shows the ideal curve, and the dashed lines show the average root mean square error for the dataset. Each blue symbol represents one alloy from the dataset. The x-axis shows its calculated liquidus temperature, and the y-axis shows its experimental temperature. The closer the point is to the solid line, the better agreement there is between calculated and experimental temperatures. If you hover your cursor over any of the symbols, you will see the composition of the alloy, as well as all of the additional information included in the data table, such as the experimental data for liquidus and solidus temperatures. You will also see the row number in the data table, making it easy to find a specific alloy in the configuration. We will now add the solidus temperature to this plot. Click the green plus sign to add another set of axes. Set the x-axis to solidus temperature and the y-axis to experimental solidus temperature Celsius, which is the other set of experimental data we uploaded. Under temperature, set the unit to Celsius again and leave the axis type as linear. Uncheck the box next to automatic scaling and set the limits from 1,360 to 1,520, stepping at 20. When you work with experimental data in the batch calculator, the program requires you to have an axis for each set of experimental data. It does not merge experimental data of the same type into one axis, as it does for calculated results. The program automatically sets a range based on the experimental data, as it did in the first plot, and it matches the range of the calculated data to that. When you only plot one set of data, the axis ranges match and the plot can be easily read. However, when you have more than one set of experimental data with different ranges, the program does not match the ranges on the axes, so the plot does not format correctly. Therefore, we must set the range manually. Uncheck the automatic scaling box under Experimental Liquidus Temperature C and set the limits from 1,360 to 1,520, stepping at 20. Finally, uncheck the automatic scaling box for experimental solidus temperature C and set the limits from 1360 to 1520, stepping at 20. Notice that the experimental axes do not have a drop-down option for temperature unit, while the calculated axis does. For batch calculations, the program uses the unit we set for the calculated results as the unit for experimental data. This is done to ensure that the units are consistent. Therefore, you must be sure that the unit you set for the calculated results matches the data you upload in the program. We recommend that you label the heading of the temperature columns so that it is clear what unit you used. Our calculation is now set, so select Perform Tree at the bottom center of the program. The experimental solidus temperature data is now shown on the plot, represented by the red triangles. The plot now also includes two y-axes, one for experimental liquidus temperature and a new one for experimental solidus temperature, together with the root mean square error for both datasets. We hope you found this video useful. You can watch additional videos at our website at thermocalc.
Всем спасибо за внимание. На этом видео закончилось по построению линии Liquidus и Solidus.